So this is question 3 on paper 1 of the 2019 paper. This is the diffraction interference question. And it was actually a little bit tricky because it doesn't ask the typical sort of question which you might have been used to doing. And it was very easy to misunderstand exactly what they were asking for, to mix up the difference between double slit and single slit interference. So let's take a look at this question and see what they were getting at. So it says that it shows us a picture with an arrangement that's investigating diffraction. And the first thing we have to notice is that in this diagram, there's only a single slit. So unlike most of the questions that you might have done when you were practicing, this is only showing a single slit, not the more typical double slit. So here we're looking at single slit diffraction, which is something that you only have to deal with qualitatively in your A-level course. I'm going to answer the question introducing a little bit of maths because it makes it, I think, a little bit easier to understand. But you don't have to know the maths, you just have to be able to analyze the pattern qualitatively. So it says, question 1, describe the pattern produced on the screen. Deceptively simple type of question, and there are particular things they're going to look for in the answer. Now, the first thing we can say is that we know that with single slit diffraction, we end up with a pattern where we have dark and bright fringes with a central fringe, something like this, where this is the intensity or the brightness of the light in the vertical direction, and we have distance from the center of our screen to either side. Now, what they're really looking for you to talk about is to compare the brightness and the width of this central fringe to the fringes. Okay, that's what they're really asking you to talk about. And this is a little bit complicated to understand in some ways if you haven't looked at the maths. So we're going to start by taking a quick look at some of the maths and look at why it is that we get this pattern when there is diffraction. So what we've got in this situation is we have a single slit, and the light is passing through this. Some of the light is going off straight through, but because the wavelength of the light is similar to the width of the slit, we're going to get diffraction or spreading out of the light. So we're going to look at the light that goes from the slit to this first point where there is destructive interference, where there is a dark fringe. So here we have the light rays heading off in that direction, coming through the slit and heading off in that direction, which will end up at that point on the screen, which is where there is destructive interference. Don't forget, it's assumed that the distance between the screen and the slit is very large. And we say this is the width of the slit. So the distance to the screen is very much larger than the width of the slit. Okay, now we've only got one wave. We've only got, unlike in the double slit experiment, and yet I'm claiming that the reason why there are dark fringes and bright fringes is because of constructive and destructive interference. So this cannot be interference with a second coherent wave because we only have one slit. So essentially we're claiming that the light is interfering with other parts of the same light. So to understand this, we can imagine that we'll divide this incoming light into little parts going through the slit. We'll say this is ray 1 up to, let's say, number 12. And what we'll say is that the first ray of light that goes through, that ends up here, destructively interferes with the 7th ray that goes through here. The second one will destructively interfere with the 8th one, the 9th one with the 10th, the 3rd one with the 10th one, and so on. So each one of those, the 1st and the 7th, destructively interfere, so we end up with a dark fringe. Now the direction of the wavefront, which is always at 90 degrees, like this, and that's heading towards that point on the screen. And we can do a little bit of trigonometry to work out, so we've got this angle, and we'd like to work out what that angle might be. Well, for destructive interference, this light ray has to have had a path difference that should be a half a wavelength longer than the path that this one took. And we know that the hypotenuse of this little triangle that I'm drawing here has to be half of the width of the slit. So I can say that the sine of that angle is equal to wavelength divided by 2 divided by slit width divided by 2, which gives me the sine of that angle is equal to the wavelength over the slit width. So what that's saying is that if I make the wavelength very, very small, then this angle would become very, very small. If I make the wavelengths larger, the angle would become larger until the wavelength equals the slit width, in which case we'd have the wave completely spreading out across the screen. The angle would be 90 degrees. Okay, right. So that's for this first dark fringe where there's destructive interference. Then we can say, so let's call that angle 1, and we can say for angle 2, well, that's going to be where the path length is now 3 wavelengths 2. That would be where it's gone this direction. So that length there would be 3 wavelengths over 2, and that would give us that the sine of this angle is equal to 3 times the wavelengths. Okay. And we can see that we can then have, we see how we can have a formula to work out the angle to any particular point. Okay, right, so once we've got that, we can now look at what that means for where we have in general what that's going to mean for our pattern. So what we have is we have the bright fringe in the center, and then we have smaller or less intense bright fringes to the side. This is our first angle, this is our second angle. Okay, so what we can see is that the middle fringe is going to be much wider than these fringes because it's made up of that angle doubled. And in fact, we could say to an approximation that the central fringe is wider, double the width of the other bright fringes. Okay, so before we finally go back to our question, we can see that when I drew this diagram, clearly most of the light is going to pass straight through the gap, the slit. So this central part, which is just due to the light shining straight through the slit, is going to be the brightest part. These other parts are caused by constructive interference of a fraction of the light that's come through the slit, so these will be less intense to the side. So now we come back to our question. Describe the pattern produced on the screen. The pattern comprises bright central maximum, which is green. With less bright fringes to either side. The central maximum is wider than the other maxima and has a higher intensity or brightness. Okay, right. Then we have the second part of this question, which says now the green filter is replaced by a red filter. Describe the change in the pattern produced on the screen. Now, again, we can say that we can understand this qualitatively, which is how we're going to answer the question. But if I go back to the mathematics, what we see is this answers the question very easily for us. We see that the angle depends on the wavelength. So when I go from green to red, that will increase the wavelength, and then hence it will increase this angle and the subsequent angles. So that means that for 2 marks, I can say that the central maximum will be wider and the other maxima fringes will be spread further apart. Okay, so all of that first 4 marks was related to this picture, figure 3, which is looking at single slit diffraction. And again, this is something that's a little bit tricky in the A-level course because it's only dealt with qualitatively, and it tends not to be something that you might have practiced very much in your questions, which are more focused on the double slit or the diffraction gratings. Okay, so we now come on to the next part of the question. So this is now a little bit more familiar. We're looking at the diffraction grating. So we placed a diffraction grating now between the red filter and the screen. It says that the diffraction grating is 500 lines per millimeter. Light is incident normally on the grating. Figure 4 shows the arrangement, so we have the arrangement here. We're told the wavelength of the red light is 650 nanometers, and we're looking to calculate the angle between a first order maximum and a central maximum. Okay, I'm a little bit stuck, not sure what to do. So what I'll do first of all is take a quick look at my data constant and equation sheet. And let me see, what I have written here is an equation for the diffraction grating that says that d sine of the angle equals n times the wavelength. So I'll just write that down. Here I've got d sine of the angle is equal to n times the wavelength. So the thing that we have to know is that what d is the slit separation in the grating. Now we haven't been given the slit separation, we've been given the number of lines per millimeter, and the slit separation d is equal to 1 over the number of lines is So therefore D is equal to 1 over 500. And the units for that were millimeters to the minus 1. So that's going to give me a value of D is equal to, and I get my calculator and I find that the answer is 1. It's going to be 1 over 500, and then converting that into meters gives me 2 by 10 to the minus 6 meters. The wavelength, I know the wavelength is equal to 650 nanometers, which means that the wavelength is equal to 6.5 by 10, 1, 2 to the minus 7 meters. And now I just simply have to plug this into the equation. The order, they tell us the order is 1, so therefore I'm going to have 2 by 10 to the minus 6 times the sine of the angle is equal to 6.5 by 10 to the minus 7. So that gives me that the sine of the angle is equal to, the sine of the angle would be equal to 6.5 by 10 to the minus 7 divided by 2 by 10 to the minus 6. So that gives me an answer of the angle of around about 19 degrees. Okay. Now the actual answer for this, when we work it out, is around 18.96. The question might be asked, why have I chosen to use two significant figures? Well, here in this part, it's given to two significant figures. So I use two significant figures in the answer. Okay. Then finally, move on to last part, and here it says, in practice the filter transmits red light with wavelengths in a range of 600 nanometers to 700 nanometers, and suggest how this affects the pattern of the maxima. Okay, so now this question has asked us about the appearance of the maxima. So in some ways it's similar to the first question. We're looking at the pattern and we're trying to decide what is it they want us to tell them about the pattern. And essentially, they're asking about what's going to happen to the central maximum, what's going to happen to the maxima on either side. So when we look at the equation for the diffraction grating, which is what we had in the last question, this is what the equation was. Now, for the central maximum, I should say, n is equal to 0. Therefore, wavelength has no effect. Okay. That maximum is in the center, the angle is equal to 0, and the wavelength is going to have no effect on that central maximum. It is going to have an effect on the maxima appearing after that. So, however, we've got the maxima of the fringes angle increases with the wavelength. And we can see that for the first one, we get the change, it's 1 times the wavelength, so we'll get that amount of increase due to the change in the wavelength. But when it's 2, it's twice that. So as we get further away, they're getting further and further spread out. So if I was to make a quick sketch, so if this is my first one, so I'm going to show this one blue. So, and then we've got, really shouldn't be so much difference between them. And then we've got the other one, and here we're going to have the central part is the same, and then they're getting more and more spread out. like so. So put this into words. We're saying that with a range of wavelengths, the central maximum is unchanged. However, first order maxima will be more spread out as there is a range of angles. Then we can say that the maximum, let's put it this way, as the order increases, succeeding maxima become more spread out, or could say broader. Okay, and that was question 3, diffraction question.